Hi everybody, this is Mark Weitzman, and I want to continue with a blog entry on quantum field theory. This will be my third one, and I'm going to be skipping a lot of material. I've been preoccupied. I haven't been posting much or making videos. I'm trying to finish Sidney Coleman's 1100-page quantum field theory book before the end of the year, and I'm at page 600, so I got 500 pages to read in a month. Probably won't be able to do it, but I'll give it a try. Anyway, I want to talk today a little bit about sort of promote the book again and give some examples of some interesting things I came across. And else you're already familiar with various aspects of quantum field theory, this video will probably be incomprehensible to you. But this is my third entry in the QFT blog, and I'm going to be doing Coleman, just talking about chapters like 25, 26, and 27. And so there's several points that, I recently reviewed in Coleman's book, and things which I hadn't thought about before, and he does everything so well. And the reason why I recommend this book is because it's lectures. So this is sort of like it's like the Feynman lectures on physics for QFT, and he really explains a lot of things that sometimes other books take for granted or don't elaborate on, and I just want to go into them. So the first thing, I'll just start right away. Let's talk about Pauli-Villars regularization. And this is on Coleman, pages 526-527. Now, before there was dimensional regularization, this was like one of the most popular methods, and it still is useful at times. Dimensional regularization doesn't always work, but this was used like in the early days by people like Feynman, and if you look at the old papers, you'll see these things. And basically the idea is that if you have a divergent diagram, it's usually some kind of loop diagram where you're integrating over d4k, and maybe you have something in the numerator and the denominator is something like k squared, let's say. And this is obviously badly divergent because we have a k cubed from the measure and k squared. But even if we have like d4k over k to the fourth, we're still a little bit of a problem, because this is like k cubed, it's like 1 over k, and it's logarithmically divergent. So sometimes you need to get extra powers of k in the denominator. And Pauli-Villars does this. It introduces sort of like, this is not crucial for understanding it, fictitious fictitious, okay, so fictitious masses. So the way in which most of you have seen it is probably along the lines of something like 1 over k squared minus m squared. K is the usual momentum variable, and we substitute instead this is equal to m squared minus lambda squared, where lambda has the dimensions of a mass and will eventually be going to infinity. And this is about 1 over k to the fourth as k goes to infinity. So your graph might converge if this works. Now, that was obvious to me. What I didn't get was a lot of times some of the books presented it in a general form. They showed this. And I didn't quite understand. I should have. I feel foolish now. I didn't quite understand what was going on with these constants and why all these extra terms and everything. But Coleman explains it quite simply. And I own a lot of QFT books, but I don't think I've seen it in any of the other ones. Probably it's there somewhere. It's maybe so obvious that they don't bother. But let's say you take 1 over k squared minus m squared, and you just rewrite it. Factor out a 1 over k squared. And eventually k is going to become infinity. And using what Coleman refers to as butcher mathematics, or non-rigorous mathematics, we're not going to worry about convergence of this series. Eventually, k will become larger than m, and so it should converge. But we have a geometric series. Now, if we apply this identity over here, we apply it to every one of these terms. Let's see what happens. We're going to get 1 over k squared minus m squared. That's this term over here. And then we're going to get, so let me rewrite the whole thing. Now we apply this identity not to every term here as well as here. So we end up getting 1 over k squared times, and we have a 1 just from here. But we're also going to get a CI from each of these terms here. So I'm going to get 1 plus the sum I equal 1 to n of CI. And then the next term, I'm going to get a plus. Let me factor out the 1 over k squared here. And I'm going to get m squared like I had before. But now from here, I'm going to get all these m squared terms. With the CI coefficient. And then keep on going. I'm going to get 1 over k to the 4th times m to the 4th plus the sum from I equal 1 to n mi to the 4th ci. And then this goes dot, dot, dot. So now you can see if we set this term, the first term, if we set that equal to 0, then our propagator has 1 over k to the 4th behavior, or better. And it was this sort of thing. I understood that, but I didn't realize that you could do better. You could set the next term also equal to 0. So basically, if you want 1 over k to the 4th behavior, you set 1 plus the sum from I equal 1 to n of ci equals 0. And if you want 1 over k to the 6th behavior, in addition to that, you set m squared plus the sum from I equal 1 to n of mi squared ci equal to 0. And it's clear that you can do that because you can make this number n as large as you want. So 2 equations, 2 variables, 3 equations, you just choose it. And just going on here, 1 over k to the 8th you set m to the fourth plus the sum from I equal 1 to n, mi to the fourth, ci equals 0. So you can get any kind of k behavior, that even k in the denominator power, that you need in order to get convergence. It's so simple, but for some reason it just went over my head when I didn't quite understand why books would show this general formula. Okay, that's just the first example I have of things that that Coleman does nicely. And now here's another also very simple thing, which probably I've seen before, but it just didn't hit me that much. So Coleman, in these chapters, he gives an excellent description of electromagnetism. Using vector fields. And he does massive electromagnetism with the Proca equation. And he relates everything, most books do this in some way, but he does it in a really elegant way. He relates conserved currents, minimal coupling, and gauge invariance. Now, I'm not going to have time to go through all that he does, but for instance, he talks about the Pauli term. Now, the Pauli term is an example of a term that's non-minimal coupling. And there's usually some coefficient. We're not going to worry about the coefficient here. Sigma are the proportional to gamma u, gamma nu minus gamma nu, gamma u. It's the tensor term in the Dirac equation, Dirac gamma matrices, F mu nu. So this is the Pauli term over here. Now, it's gauge invariant. Because FUV is. And but it's not renormalizable. Not in 4 dimensions. And you can see that because it has a mass dimension. Three halves for the first psi, 3 halves for the second psi, and 2 for the FU nu. That's equal to, I think I got that wrong. Yeah, okay, that's equal to 5. So which is greater than 4. So it's not going to be renormalizable. But otherwise, it's okay. Now the interesting thing is, how's a better way to understand that? And one of the ways to understand it is to, if you look at something like, let's say you look at a term. It's easy to imagine a term like this. And if you integrate that by parts, you would end up getting Now, this vanishes, okay, because sigma u nu is anisymmetric. And partial mu, partial nu is symmetric. So that term vanishes, but here's where I hadn't, I guess I've seen this before, but I just didn't remember it. But let's say we take this term that vanishes and we apply minimal coupling. Then we get d mu psi bar sigma mu nu d nu psi. And again, by integration by parts, we're going to get minus psi bar sigma u nu d mu d nu psi. And remember the definition of the covariant derivative. Or the minimal coupling prescription. So we have this. And now what's interesting is that d mu d nu is not symmetric. So this term doesn't vanish. So let's just show really quickly that this term is not symmetric. Let's compute the commutator. This is a trivial computation, but I'll show it. Minus mu exchange with the index nu. So this is going to be equal to the partial of mu, partial of nu psi, plus IE, partial of mu a nu, acting on psi, plus IE a nu, the partial of mu psi, plus IE minus E squared a mu a nu psi minus mu goes to nu. Basically, we did everything. You would think there are 4 terms here, but I left this out here. We're applying it to psi. And when we take the derivative, sometimes we take the derivative of psi, and sometimes we take the derivative of a. So it adds an extra term, and it's easy to see. Now, because of the minus mu goes to nu, anything that's symmetric in this vanishes. So this vanishes. This vanishes. These 2 terms are symmetric, so they vanish. And we're only left with d mu, d nu minus d nu, d mu psi is equal to IE partial mu a nu minus partial nu a mu psi, which is equal to IE f mu nu psi. So that's great. So basically, so psi bar sigma mu nu d mu, d nu psi is going to be proportional to psi bar sigma mu nu psi f mu nu. I'm sorry, these should be upstairs. Which is the Pauli term. So it's nice that we can think of the Pauli term as just being the term that arises on covariant derivatives of terms that normally vanish. Not a big deal, but it's just nice to know. Now, what Coleman does really well in these chapters is he explains the technical difficulties. A lot of books just like gloss over these. In canonically, I know that's not spelled right. Canonically quantizing gauge theories. And also theories with derivative coupling. And, a lot of books, when they do like scalar electromagnetism, they'll give this vertex, and they'll give the rules. I won't even write them down here because I'll probably write them down wrong, but they're pretty simple. But they come out of nowhere, it seems. They do come out of the Dyson-Wick formalism and everything, but you have some technical difficulties that you have to overcome. And one of the first things is that when you have derivative couplings, for example, you'll often find that the interaction Hamiltonian is not equal to minus the Lagrangian interaction. And this can have disastrous results sometimes. And often you end up with non-covariant terms. And Coleman gives an example, and he shows, I'm not going to do it here, but he shows that you can end up very easily with a term like psi bar gamma 0 gamma 5 psi squared, which is non-covariant. Because of the because it picks out the time gamma 0. So that's like an example. And so you end up getting a non-Lorentz invariant theory. And also he points out that you also get problems with the contraction terms. So you'll get terms like when you do a contraction, And again, he works this out. See, because you have derivative couplings, you're going to get all kinds of things like this. And you're going to end up getting some kind of term like now this term is good. This is covariant. But you're also going to get another term. This term is bad. Again, singles out. 0 components. So turns out, Coleman doesn't show this, but he points it out. Cure each other. And he goes through the whole discussion, for more discussions. On Hamiltonian method. Initial condition. And gauge redundancy. Etc. Read these chapters. And that's mostly what I want to say today. Again, I really like Coleman's book. Another aspect, which I'll just show briefly, that's like a problem in Coleman's book where he derives the Hamiltonian for the electromagnetic field in the massive case. R as, if you look at the formula on the very bottom, as 15.16, he just gets it as you can see it's just, well, actually I don't, let me see if I can get the formula. There it is. So this formula here, the sum over R are the polarizations, A dagger R, A R K. That's, everybody knows that's the answer, but to do the calculation, it's not hard, but he does it in one page, very detailed everything. So he's got a lot of great problems like that, and all I can say is that I highly recommend this book. A lot of the things that other books sort of gloss over, and right after these chapters, Coleman goes into path integral methods, functional methods, which surmount all these problems. And in other books, sometimes they start with the functional methods. They sort of ignore the canonical method. But as Weinberg points out in his quantum field theory book, you sort of need both methods. Some methods, it's easy to show that the theory is unitary. In other methods, it's easy to show that it's Lorentz invariant. In other methods, it's easy to show that it's renormalizable. But there's no method which does all three at once. And that's sort of like one of the interesting technical difficulties of quantum field theory. So, as I said, I'm going to try and finish Coleman's book, and then I'm going to go back to Peskin and Schroeder and resume blogging with Chapter 3 and so on, a little bit on each chapter to go through that book as well. Thank you very much. I'll see you next time.